kitu yangu bwana.
Ulikuwa unataka kuweka hapo?
It's okay.
Hapa tunasomea hapa. Okay, so learners, we're back with our demonstration or a video demonstration on how this electromagnetic spectrum is usually produced. Now, as you can see from the screen, we have
electromagnetic waves are those in which magnetic and electric fields oscillate perpendicular to each other. In this electromagnetic spectrum, the waves are arranged in the order of increasing frequency. You can see an example for each band of the electromagnetic spectrum by taking your mouse over it.
So we are going to, you can see the arrangement of the waves here from the radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and the gamma rays. Now we have seen from here, you can see the wavelength in meters. They're ranging from 1, or the radio waves range from 1 meter to 1 to power 4 meters, and going on to up to the gamma rays, which have the smallest wavelength of 10 into power 12 meters. Now, we are going to put a mouse, or we'll be placing the mouse over each wave to see the application in a very short while. Here you can see when I place the mouse here, it is showing us a radio waves. This is a radio. Most of us may not be aware of this radio, but they are there at home. You can look at it. And radio waves are not only applied in radios, they are still the same waves that we use in our TVs, in our phones. When you make a call, we use the radio waves. Then we have the microwaves. You can see a microwave. I believe most homes have a microwave. Then we have the infrared. Majorly they are used in supermarkets. When you're buying stuff in a supermarket, there is that device that they use. It uses the infrared to record the barcodes of the prices. Also, your phone, when using something like Bluetooth, your remote, the remote of your TV, like this one, they use infrared. Then we have the visible light. The visible light, all of you are aware, it's the one that you used to see, the animals used to see, and the plants used to make food through photosynthesis. Then you have ultraviolet rays. Majorly they are used as a disinfectant in water production and other places where we disinfect. We use ultraviolet rays. We are going to look at the hazards of these waves. Actually, from the ultraviolet rays, X-rays, and gamma, you're going to see even the hazards, because they have their own applications, but they are also hazardous when they are exposed to, when persons or people are exposed to them. Then we have the X-rays. Here you can see a whole kind of a structure of X-ray. Most of us have maybe experienced this. X-rays are used majorly in medicine, in X-ray photography, in our hospitals, and they used to check internal body organs, body fractures like a broken rib, a broken leg. They're also used in our airports, in security checks. They are also used in industries. We're going to look at the application later. Then we have the gamma rays. The gamma rays are also called the Y rays. They're also used to check internal body organs. You can see like this one. This person is being checked the internal body organs. However, it is not so much recommended to use gamma photography because of the dangers that are involved in them. Gamma rays are also used in industries to check flows in metals. They are also used in our airports for security checkup and all those kind of things. We're going to look at them later. So simply this shows the electromagnetic spectrum from the longest wave to the shortest wave, or the waves with very small frequency to waves with very high frequency, or the waves with very little energy to waves with very high energy. I get now. I mean, I believe by now you are getting the spectrum, the band, the width. Now, next, I want us to look at the interaction between magnetic field and electric field. So this is how they interact. What's this one?
Electromagnetic. Electromagnetic waves consist of oscillating electric and magnetic fields, each sustaining the other. This means that an oscillating electric field also produces an oscillating magnetic field. The oscillating magnetic field, in turn, produces an oscillating electric field. This process is self-sustaining. For all practical purposes, electromagnetic radiation is considered to be a progressive transverse wave.
Okay, guys, again, you can see here we have, like we had said, if this is the electric, this one is the electric wave or electric field interacting with a magnetic field, they produce an electromagnetic wave here, this is Z here, and then you can see how it is, they're interacting, and the wave is now moving in this direction as I'm showing my mouse here. You can see that. And actually, at higher levels, you're going to, maybe those who take physics at higher levels, you study the electromagnetic dynamics, something like that, and you're going to study more on this. So for now, let's just know that when electric fields and magnetic fields interact, they produce an electromagnetic wave. Now, from here, I want us to look at or to go through some of the properties of electromagnetic waves, and we can go back to our board.
The electromagnetic oscillations produced in a resonant...
We can come back to our board here, so that we just move there. All right. So welcome back to our board. Look at some of the properties of electromagnetic waves. Now, I usually tell the student that the easiest way to know the properties of electromagnetic waves is if you can be able to know the properties of visible light. Why? Because visible light is part of the electromagnetic spectrum. Therefore, since this visible light or light itself is an electromagnetic wave, then all the properties of light will also be the same properties for, sorry for that. There are challenges that we're having in the house, but you're trying to improve it. Time to be able to improve it. Just can check it up. Can pause. Good. Can you go on?
Can go.
All right. So I was saying, before the phone fell off, we're recording with our phones. We're using the available materials that we can be able to use. Now, one property of all electromagnetic spectrum waves is that they move with the speed of light. So they travel. They travel with speed of light. Travel with the speed of light. And all of us, as physics students, we know the speed of light. The speed of light, c is usually given by 3.0 times 10 into power 8 meters per second. So all of them will be traveling through space with this speed. And by the way, I must remind you something, that we said that electromagnetic waves, all of them, they are transverse in nature. They are transverse in nature. And that means that when they are moving, the direction of the wave is perpendicular to the oscillation of the particles, so that it will look like this. So property number 2 is that all these waves are transverse in nature. Transverse in nature. And another property is that, remember, from our definition, actually from Form 2, we said electromagnetic waves do not require material media. So another property is that they do not require material medium for transmission. They do not require material medium for transformation. And that's why look at visible light. Visible light will, the major source of visible light is the sun. And between the sun and the earth, there is a very big vacuum or space that this light have to travel from the sun until they get the earth, where we now use them to see and the plant use them to make their own food. Therefore, it is true that they do not require material medium. And this, I must remind you that the other type of the waves or the mechanical wave would require the material medium, something like sound. Sound is a mechanical wave, and that's why sound does not travel through vacuum. In Form 2, you're able to see that when you're looking at sound. The other property of electromagnetic waves is that they undergo the following phenomena. One of them is that they undergo one, diffraction. They undergo refraction, diffraction, and interference. Now, look at this. All these waves will undergo refraction. This is what we studied in Form 1. In diffraction in plane mirrors. That is rectilinear propagation of light. We're able to look at reflection. Then in Form 3, diffraction of light, we're able to look at refractions. Then in waves 2, we were able to look at diffraction and interference. Now, you can see, since all of them are undergoing these, then it is true again to say that they undergo or they have the properties of light. The other property of these waves is that they do not possess charge. They do not possess charge. They are chargeless. They do not possess charge, and therefore they are not deflected by either magnetic fields or electric fields. Right? So when we'll be looking at mostly in the cathode rays and the X-rays later in the year, or later in our syllabus, we're going to look at how diffraction takes place. But all electromagnetic waves are not reflected or deflected by either magnetic field or electric fields. Then they possess energy. That's another property. So these waves will possess energy. So we say, number 6, all of them, they possess energy. Okay? Now, we say that light is a form of energy that enables the eye to see. So all of them, they possess energy. That we call light as a form of energy. Now, the energy in a wave is usually given by an equation. E is equal to hf, where h is the Planck's constant. The Planck's constant, we're going to introduce it later in atomic physics, in X-rays and photoelectric emissions. We're going to look at the Planck's constant in more detailed manner. Then we have f is the frequency of the wave. So in this case, our Planck's constant has got a value. It's a constant. Therefore, it does not change, and it's usually given by 6.63 times 10 into power 34 joules second. So yeah, we'll come to talk about this more when we're looking at nuclear and atomic physics later in our syllabus. Now, you're going to look at one example on how you can be able to calculate the energy possessed in a wave. And I'm going to use a very simple example. Just keep following with me. Sorry. Okay, so I'm going to give an example. I'll write it here. but I'll write the values. So if you have maybe a red or a green light of wavelength, a green light of wavelength 5 times 10 into power negative 10 meters, 10 into power 5 meters. So we are given the wavelength actually, and then we're told calculate the energy. We calculate the energy here. So our solution B, if you can look here in this equation here, the only value that we're given is the wavelength. And we have seen from our equation of calculation of energy in a wave, usually given by E is equals to HF. We know H is 6.63 times 10 into power 34 joules second. That is our constant. You can see in our equation here we are not given the frequency. However, we know that we can get frequency from the equation of V over H over lambda, sorry. V lambda. You know, remember this equation from form 2? V is given by F lambda. So we know the speed. We said all these waves travel at a constant speed of light, which is 3.0 times 10 into power 8 meters per second. So in this case, we have the velocity, we have the wavelength lambda. So what we can be able to get here, we can be able to get the frequency, so that when we obtain the frequency, now we can come back to our equation and get the energy. So we're going to do that. Grab this. Now, our frequency will be given by V over lambda. Then we have 3.0 times 10 to the power 8 meters per second divided by, it was 10, it was 5 times 10 into the power 5 meters. So we're able to divide that. We get, I'm required to use a calculator here. Let me use my phone as a calculator to get the values. So kindly, we are doing this together. If you have a calculator, you can do it with me. So we have 3 times 10 into the power 8. I'm using my phone. It's not scientific. So divided by 5 times 10 into power negative 5. It's giving me an error. We have 6.0 times 10 into power 14 hertz. So that's our frequency. So this is our frequency. And now since we have our frequency here, then we can be able to get the energy. Our energy now will be given by E is equals to HF. We have the Planck's constant, 6.63 times 10 into power 34 joules seconds. Then multiplied by 6.0 times 10 into power 14 hertz. These are joules second. Therefore, our answer would be 3.978 times 10 into power negative 19 joules. So this is the energy possessed by that wave. As it is moving through space, it carries with it this amount of energy in joules. So that is an example of a question that you can be asked to calculate the energy processed in a wave. So in our next class, we are going to look at the production of these waves and how they are applied. So our next class, we'll be able to finish the topic by looking at one at the production and how we can be able to detect them, and finally how they are applied in our real life situation. And also we look at the hazards they possess, particularly when they have a lot of energy. And also look for a video to show you different production of these waves, including X-rays, gamma rays, because we're not so, we've not interacted so much with them. So thank you for now. Yeah, I'm going to attach assignment in our group so that we can do a few questions of what we've studied today. Thank you so much.